So now we are going to discuss about dielectric materials. First, what is dielectric materials? Dielectric materials that can be defined as follows. Those solids which have an energy gap of 3 electron volt or more than 3 electron volt are termed as insulators. In these materials, it is almost not possible to excite the electron from the valence band to conduction band by applying external electric field. Generally, dielectrics are also called as insulators, thereby poor conductors of electricity. However, they allow movement of some electrons at abnormal high temperatures, causing a small flow of current. Dielectrics are non-metallic materials of high specific resistance, negative temperature coefficient of resistance, large and insulation resistance. Insulation resistance will be affected by moisture, air temperature, the applied field and the age of dielectric materials. Dielectric materials are electrically non-conducting materials such as glass, ebonite, mica, rubber, wood and paper. These are the examples for dielectric materials. All dielectric materials are insulators. The difference between a dielectric and an insulator lies in the applications. If the main function of non-conducting materials is to provide electrical insulation, then they are called as insulators. On the other hand, if the main function of non-conducting materials is to store the electrical charges, then they are called as dielectrics. The general properties: generally dielectrics are non-metallic materials of high resistivity. They have a large energy gap, more than 3 electron volt. All the electrons in dielectrics are tightly bound to their parent nucleus. As there are no free electrons to carry a current, the electrical conductivity of dielectric is very low. They have negative temperature of coefficient and high insulation resistance. Fundamentals of dielectrics and definitions and properties of electric dipoles. You see the diagram. When we are keeping it two different dissimilar charges in a particular distance, then it is called as dipole moment. The product of magnitude of charges and the distance between two charges is called as dipole moment. Permittivity. Permittivity represents the dielectric property of the medium, which indicates easily polarizable nature of the given material. Unit of permittivity is farad per meter. Dielectric constant. The dielectric characteristics of material is defined by its dielectric constant. It is a measure of polarization of dielectrics. It is the ratio between absolute permittivity and permittivity of a free space. It's similar like a permeability that we have discussed in the last unit, magnetic materials. In the case of magnetic material, it is called as permeability, whereas in dielectrics, it is permittivity. So the dielectric constant is absolute ratio of absolute permittivity and the permittivity of free space. Polarization. The process of producing electric dipoles inside the dielectric by the application of external electric field is called polarization in dielectrics. Again, we are going to discuss about the polarizability. It is found that average dipole moment field mu is directly proportional to applied electric field. Mu is nothing but polarizability, dipole moment. The dipole moment is directly proportional to applied external electric field. When we are introducing a proportionality constant alpha, then it is called as polarizability. Polarizability is defined as the ratio of the average dipole moment to applied electric field. The unit of polarizability is farad meter square. Polarization vector. It is defined as the average dipole moment per unit volume of a dielectric. If n is the number of atoms per unit volume of a dielectric and mu is the average dipole moment per atom, then electric flux density is defined as the number of electric flux passing through a medium unit area perpendicular to the direction of flux. Electric flux density is a measure of strength of an electric field generated by a free electric charge. D is equal to epsilon r epsilon 0 into E. The unit of this is coulomb per meter square. Polarization measures the additional flux density arising from the presence of materials as compared to free space. It has been same unit as electric flux density. Next one is electric susceptibility. Electric susceptibility is a quantitative measure of the extent to which an electric field to a dielectric medium causes polarization. The slight displacement of positive and negative charges within the medium or material is called as dielectric susceptibility. P is equal to epsilon 0 and psi E. E. Psi E is called electronic susceptibility. The ratio between permittivity and susceptibility that we are going to discuss. Susceptibility is equal to P divided by epsilon E. We know the value for P by epsilon R. So by substituting those equations, then we will get susceptibility is equal to epsilon R relative permeability minus 1. Next, we are going to discuss about types of polarization. When a dielectric medium kept under electric field, what are the ways it can be polarized? Like a magnetic material under magnetic field, how it will be magnetized? Similarly, here instead of magnetic field, here we are applying electric field. Instead of magnetic material, ferromagnetic material, here we are keeping dielectric materials. Dielectric polarization occurs due to the several microscopic mechanisms. It can be classified into various types. First one is electronic polarization. Second one is ionic polarization. Third one is orientation polarization. Fourth one is space charge polarization. So what is electronic polarization? See the diagram. When there is no external electric field, how all these different kind of polarizations are there in a material, electric material. When you apply a electric field, how these positive and negative charges can be aligned under electric field. First one is monatomic atom. There is a nucleus at the center, the electrons are roaming around the nucleus.